So in this video, we're going to talk about equilibrium uh, conditions that makes a body stay in place, not don't move. So an easy one that you can think of is the net force is zero. All the forces add up to zero, then the body is going to be in equilibrium. But that's not enough. We need one more condition now that we know torque. And let me show you a picture here. So we have this box. And then this box has these two forces, this pointing this way and this pointing the other way. They cancel out, and this is going to be in equilibrium. However, what if I apply these boxes a little bit off center, right? So what is happening is this thing is going to rotate. So even though there's not going to be a neck translation, either left or right, this thing is going to start spinning. So we would say this is not in equilibrium. So to have equilibrium, we need two conditions. We need net force equal to zero, but we also need net torque equal to zero. This guarantees that there is no translation, and this guarantees that there's no rotation. And those are the two conditions for equilibrium. So now when let's look at one example here and how we would solve problems with equilibrium. So we want this. We have this strong man, and then he wants to keep this 1 ton thing suspended, right? So then this is your pivot here, and he's applying a force here, right? And there is a force here. And we're going to consider that this bar is lightweight, so we're going to neglect the weight of the bar compared to the bucket. And so this distance here is given to you is 3.6 meters. And then we want to know this force. How much force does he need to apply? So we draw a free body diagram. So this is your pivot. And then the force from the bucket, the force from the man, and so this is what we want to find. So we need to apply the condition for equilibrium. Condition for equilibrium is the addition of all these forces equals zero, and the addition of all the torques produced by these forces about a pivot, which we are choosing to be this, that should also equal zero. So we have the force from the bucket, which is the weight. We have the distance from the bucket to the pivot, and we have the distance from the man to the pivot. So let's just find the forces. So the force from the bucket is just mg, so that is this number here. So then we have an equation for equilibrium for the forces, and we have an equation for equilibrium for the torques. So what are the torques? Well, the torque is the torque due to the bucket, which is the force from the bucket times the distance from the bucket to the pivot, and then the force from the man times the distance from the man to the pivot. And these two have to add to zero, and from there you get the force from the man, which is 2100 newtons. So that's equivalent to 3 people, right? So now we have the force from the man, and we can find the force at the pivot. And the force at the pivot is going to be, well, you can use the net force equals zero to solve for that, and that's going to give you 6,800 newtons. So when we solve these equilibrium problems, you have the freedom to choose the rotation point that we call pivot. So that's what we did there. So typically you want to choose this point to simplify your equations, right? So any pivot will work, but some will make your life way easier. So for instance here, well, you have a tension here, and you have a center of mass here of force, and you have a normal force there. So you could choose a pivot about this point, or a pivot about a point here, that'll work. or about this point. In this case, probably this one would be the easiest one because this force you don't know well. And if you choose a pivot here, when you write the torque equation, well, this force doesn't produce any torque about this pivot, so that force is not going to appear in your equations, and it's going to simplify your life. So let's look at one example here, one more example. So you have a scale here, and you have 100 newtons here. What is the reading on this scale? And this is halfway, right? This is L over 2. So we're going to choose the pivot here because, well, there are forces here, but we are not interested in those forces. So then we have the force on the scale times L over 2 minus, right, the force from the weight, which is 1000 newtons times L, and that have to be equal to 0, right? So these are the two torques. So now we can cancel the L's, and then we get that the force on the scale is equal to what? Is equal to 2 times 1000 newtons. So that's how you're gonna solve this problem. So let's do one more problem to see how we treat these equilibrium problems. Here we have a bar, right? So this bar is right there standing against the wall, and there's some friction here. And so this angle is 60 degrees. And then we want to find the minimum friction coefficient so this thing doesn't slide, right? Doesn't go and fall. So we are going to neglect the friction at this point. We're going to count the friction here. So this is your free body diagram, right? So you have, what are the forces? You have a friction here. You have a normal force here. You have the weight. And you have a normal force here. You don't have anything else. We can start by calculating these distances here, this d2, right? So d2 is L sine theta, and L is given to you, right? So L is 3 meters, is given to you, so you got d2. And d1 is this distance here, right? From the center of mass to this point here, d1 is 1/2 L cosine theta, right? So this thing is going to stay in place if the friction is less than the maximum friction. There is a maximum friction that you can apply here, which is the friction coefficient times the normal. So this thing is going to stay in place if this friction is always less than this. It's going to just start, if this condition stays, well, then it's going to still stay in place, but that's the maximum condition. And then as soon as this force, as soon as this changes, this is no longer true, then this thing is going to start moving. So let's see now how to treat this problem. We're going to start by writing the torque equation. So the easiest pivot here would be this guy here, right? Because you have two forces applied at this point. So these two forces don't do any torque about this point here. So that's your best pivot there. So if we choose that, then we have the torque due to gravity, which is d1w, minus the torque due to the normal force, which is d2n2. And so that's those are the torques. So we got those. So now we can solve for N2 from this equation, right? We can solve for N2. So we rewrite the equation here by using our equations for D1 and D2. We put them there. So, and we solve for N2, and N2 is the weight of the bar times 2 tangents of 60 degrees. So now let's apply the equilibrium condition for the forces. N2 minus the friction have to be equal to 0, and N1 minus the weight have to be equal to 0. So therefore N1 is equal to the weight, and then the friction is equal to N2. So now we can rearrange these equations, right? So we can put N2 here and the weight there, and then we get that the friction have to be equal. So to get the friction that we need, so the friction has to be equal to this thing here, and this has to be always less than the maximum friction. And then from there, you can identify your friction coefficient, which is 1/2 tangent of 60 degrees.